Hello, can everyone hear me? Just need someone to confirm if the audio is all okay. Okay, thank you. All right. All right, welcome guys. We'll be starting shortly. Okay, you should all be able to see the screen moving right now. Is that all good? Okay. All right, let's get started. We'll let anyone else filter in. Just some points about today. So we'll be going pretty quickly, about 30 seconds of thinking time, and then I'll walk you through the questions. We will skip some questions if we need, just do a time. And if you have any questions in the middle of the session or in the end session, just email us. All right. Make sure your mic is muted as well. Don't want any audio getting through. And if you have any issues, just give that number a call. Okay. He'll sort you out. At the end, you can scan the QR code in order to get this PowerPoint to you. Okay. I'll get started. Make sure you have a paper and pen in case you have any questions. So write them down at the end. You can ask me. All right. And again, so don't copy anything. I'll be giving you this PDF at the end, and take notes if you really need. All right. Of course, once you get the PowerPoint, you can try it on your own. All right. And there's also a mock exam for you at the end. All right. Okay. So I'll be taking you through kinematics and dynamics. All right. So kinematics is all about motion, vectors, forces. All right. So let's define some terms first. Now you should all be familiar with these already, but it's all revision. Okay, so scalar quantity is a quantity that's only going to specify magnitude. So things like speed, things like mass, all right, they can have a magnitude, but they don't need a direction. Okay. Now a vector is the opposite. It has magnitude and a direction. All right. We know what distance is, displacement, average velocity, and instantaneous velocity. I want you guys to note they are distinctly different because the average velocity is the change in displacement over a fixed period of time, okay? And the instantaneous velocity is the velocity at a particular instant in time, okay? And we'll see how that works out in examples, all right? And uniform acceleration is just the uniform rate of change of the velocity vector, okay? Should all be old stuff for you guys, okay? Okay, so there's a few equations that we're going to start off with immediately. That's the non-accelerated equations and the accelerated equations. The non-accelerated is essentially just the equation for average velocity over a certain time period given by speed over time. And these other three we'll look at in a bit more depth in a minute. Okay, but these are your Suvat equations, which we'll use a lot pretty soon. Okay. All right. Example 1. Okay. A person observes a firework display from a safe distance of 0.75 kilometers. Assuming that sound travels at 340 meters per second in the air, what is the time between the person seeing and hearing a fireworks explosion? Okay, so we're given a distance between a person and the fireworks, and we're also given a speed. Okay, first thing we'll do in any question is draw a little diagram. Okay, so I'll draw up a very rough diagram. Okay, here's F for the fireworks and here's P for the person. Okay, this is 0.75 kilometers. All right. And we know that the speed of sound is going to be 340 meters per second. Okay. So to find the time between the person seeing and hearing the firework explosion, what we're going to do is we're going to divide the distance the sound has to cover with its velocity. All right. So distance equals speed on time. Very basic formula. Now the speed is given in meters per second. Okay. Sorry, velocity on time, my bad. The velocity is given in meters per second, all right? We've got to be very careful with the units here, okay? 340 meters per second. Now, the displacement is given, or the distance is given in kilometers. We have to convert that to meters in order for our calculation to make sense, okay? So 0.75 kilometers, very simply, is 750 meters. Now, if we put that in your calculator, you get a time of 0.45 seconds. Okay. And I'm going to leave that to 2 significant figures because the rest of the question has only given you values with 2 sig figs. Okay. All right. Example 2, a student states that the speedometer in a car measures the velocity of the car at any point in time. Assess the correctness of this statement. Okay, so it's a worded question here, and we're being asked to assess how correct the student's statement is. All right. So he's saying that the speedometer is going to measure the velocity at any point in time. It's a bit of a tricky statement to decode, but the reason this guy's statement is wrong, okay, is because he specified velocity. Okay. So if you guys have seen your car, if you're else, you'll know that the speedometer is going to show a number for velocity or speed rather, okay? But here in the question, in the statement, he's saying that the velocity of the car is shown, okay? Velocity is a vector quantity, okay? A vector quantity has both a magnitude and a direction, but your speedometer can't show direction, only magnitude, okay? So the statement will be incorrect because the student has stated that the speedometer will measure velocity when in actuality it's the speed. Okay. Next question. A car travels 90 meters due north in 15 seconds. Then the car turns around and travels 40 meters due south in 5 seconds. Okay. So we've got 2 portions of motion here, and we're being asked to calculate the magnitude of the average velocity during a 20-second interval. Okay. Now, average velocity is distinct from instantaneous velocity in that we're taking the entire motion and taking its average velocity and not at any of these individual moments. All right. So what we do, okay, is recognize that velocity is to do with direction, meaning the 90 meters north and the 40 meters south are going to interact. What that means is moving 90 meters north and then 40 meters south, okay, will result in an average displacement of 50 meters north, okay? So the average velocity will be the displacement on time, or the total displacement on time, which is 50 over 20, okay? So the average velocity will work out to be 2.5 meters per second north, all right? Like I said, velocity is a vector quantity. We need a magnitude and a direction. In our case, the direction is north, okay? Just to remind you guys, any questions, make sure you note down your head or in a book, and in the middle break between the modules, you can ask me, all right? Next question, in a 4-kilometer race, a runner completes the first kilometer in 5.9 minutes, the second kilometer in 6.2 minutes, and the third kilometer in 6.3. The final kilometer in 6 minutes. The average speed of the runner for this race is approximately, okay? So here we're asked for the average speed, okay? So average speed is not a vector quantity, meaning the direction does not matter, all right? So the direction this runner is running is not important to us. All we're concerned about is how far they're running, okay? So speed average, all right, is going to be total distance covered over the time. Okay. So pretty simple. We're adding up these little segments of motion. The first portion, the first kilometer, well, very simply, it's going to be 4 portions of 1 kilometer, right? So we can put the total distance being 4 kilometers. Okay. And we have the total time, okay, which is going to be 5.9 minutes plus 6.2 minutes plus 6.3 minutes. And the final kilometer in 6 minutes. Okay. That works out to be 4 over 24.4, or an average speed of 0.116 meters per second. Sorry, that'd be kilometers per minute, my bad. Now, we don't always have to leave our answer in meters per second. It's preferred, but in this case, it's not an issue, okay? Although, to be safe in an exam, I would convert to meters per second, all right? So as you can see, there's a very important difference between average velocity and average speed, okay? Average velocity takes into account direction, average speed doesn't, okay? All right, next question features a graph, all right? Ben drove 60 kilometers from his home to Liverpool. He stopped and visited his friend Tim on the way. Work out Ben's speed for the first part of his journey. So we're given a graph of distance from home versus the time of day, all right? And we can see that there's a period of motion here, followed by some stagnancy, probably where he's at his friend's house. And the last portion is probably his second leg of his journey to Liverpool, okay? So his speed for the first part of his journey, okay? Speed will be equal to distance over time. And in our case, it's just gonna be the gradient for this graph because the gradient is m equals rise over run. The rise in this case is distance, run is time. All right, so we'll pick these 2 points. All right, so that's going to be 30 minus 0 on 14 hours minus 1300 hours. Okay, so that's 24-hour time. I'm going to leave it like that. All right, so in total, it's 30 over 1, or in other words, 30 kilometers per hour, okay? Now, the gradient of this graph is just gonna be y2 minus y1 on x2 minus x1, but that's just some basic maths. So if you have any questions around that, you can ask me at the end as well, okay? All right. Okay. So now we come to our Suvat equations, or this is just a handy way of memorizing the letters, all right? For any objects which are uniformly accelerated, we can use this method to solve problems. That means if we have a question or any setup that has a uniform acceleration, meaning the acceleration won't change, these equations are all valid, all right? They are not valid if the acceleration changes, but you won't really come across that in this module, okay? So these should be pretty quick to memorize. I'm sure you've got most of these down already, all right? But you'll see that they're pretty useful for different questions, all right? So a car traveling at a speed of 30 meters per second encounters an emergency and comes to a complete stop. How much time will it take for the car to stop if it decelerates at 4 meters per second? Now, with any of these questions that are featuring rectilinear motion, okay, so motion in a line that has velocity and a constant acceleration, always write out the variables you're given before you start the question, okay? So a car is traveling at a speed of 30 meters per second. That's our initial velocity, okay? So above that, we can write a little u to represent initial velocity. It comes to a complete stop. That's giving you your final velocity in a sneaky way. It's not telling you that it's a 0 meters per second velocity, but it's telling you by the end of the motion, we're going to have no velocity, all right? So there's our v. How much time will it take for the car to stop? So we're being asked for the time. If it decelerates at 4 meters per second, we're given the acceleration there, all right? Or -4 is our acceleration, all right? So we have 4 variables we're working with, v, u, a, and t, okay? Now, if we look back on our equations, we can see that one of them pretty neatly aligns with what we have, all right? The v equals u plus at equation. So we'll chuck this one in. V equals u plus at. Now we're finding t, so we're going to end up making it the subject, but let's just put in what we know first and see where we can go from there, okay? So the final velocity is 0. The initial velocity is 30 meters per second. The acceleration is -4 because it's a deceleration, meaning it's against the direction of motion, all right? So we can represent this as being -4, and the time is what we're finding, okay? So if I rearrange this, I'm getting 30 minus 4t equals 0. Then if we make 4t the subject, 4t equals 30, all right? And then divide both sides by 4, we get t is equal to 30 on 4, or 7.5 seconds, okay? Pretty straightforward, guys. All right. To summarize, write out all the variables you're given first, then choose an equation, and then from there, you can work out what you need to. Okay. And this method is pretty much infallible. Even the hardest questions, as long as you know exactly what you have, you can figure out on approach 4. All right, number 2, a particle is accelerated from 1 meters per second to 5 meters per second over a distance of 15 meters. Find the acceleration and the time taken. Okay. So a few variables here again. We're given the acceleration as a question. So we're finding the acceleration. We're finding the time, and we're given the initial and final velocities. Okay. So we have again V, U, A, and T, except we're being asked for 2 variables. Okay. So we'll write out the first equation we know we'll use. V equals U plus AT. Okay. And we're also given this final little extra number, which is distance, or in this case, because it's in one direction, sorry, excuse me, it can also be taken as a displacement. We also have S, okay? So we have V, U, S, A, and T. Now, in our case now, we have all the variables, okay? So we can use any of the 3 equations. But I have a feeling that this one right here is going to be also useful to us, okay? So let's chuck this one in as well. V squared equals U squared plus 2AS. Okay, now let's see what we've got to work with. All right, call this equation 1 and equation 2. In equation 1, we have V as being 5. So 5 equals U, which is 1, plus AT, which we're finding. Okay. In equation 2, we have V squared, which is 5 squared, equals U squared, which is 1 squared, okay, plus 2AS, so plus 2A times the displacement again, which is, 15. Okay, so let me rewrite this S here, this 5 here properly. 5. Okay. So in this equation, we have the unknown as A, all right? And I'm thinking if we can find A from this equation, we can sub it into this one to find T, okay? So a pretty standard approach using some simultaneous equations, all right? So equation 2 will tell us that 25 equals to 1 plus 30A. Now, if I skip a few steps, I'm going to get A is equal to 24 on 30, okay? And we'll leave it as that. Call this number 3. Now, 3 into 1. So let me resize some of this stuff, guys. Oops. Just going to move this over here. That's fine, we'll do. Okay. So we have our acceleration now, okay? Equation 3 back into equation 1, okay? It's going to give us 5 equals 1 plus 24 on 30 times time, okay? So now we've got acceleration, we can find time, all right? 24 on 30 in decimals is 0.8. So 4 equals to 0.8 t, and therefore time is 4 divided by 0.8, which is 5 seconds. So we have acceleration as being 0.8 meters per second squared in the positive direction, and time being time. So it's important to put in a final direction for your answer because acceleration is a vector quantity, and saying the positive direction just means in the direction of motion. As we can see, the particle is being increased in velocity, meaning the acceleration is in the direction of motion in order to make the velocity faster. So we can say in a positive direction to mean the same thing, okay? All right, number 3, a car is being driven along a road at 25 meters per second when the driver suddenly notices that there is a fallen tree blocking the road 65 meters ahead. The driver immediately applies the brakes, giving the car a constant retardation of 5 meters per second. How far in front of the tree does the car come to rest? Okay, so a bigger question now, but the same process. Let's go through and find which variables we have. All right. A car is being driven along a road at 25 meters per second. That's our initial velocity here. All right. The driver notices the tree 65 meters ahead. Okay. So that's part of the displacement. I won't write what this is yet. It's a more complex example. All right. The driver applies the brakes, giving the car a constant deceleration of 5. There's our A. Okay. Let's draw a little diagram to represent our situation. So here's our tree. Here's the car, okay? All right, it has a velocity initially of 25. And this distance is 65 meters, okay? All right, so what we're really finding first is how far the car travels to stop, which we'll call S, okay? And then the final answer is going to be D. So we're being asked for how far in front of the tree does the car come to rest. That's neither 65 or S. It's going to be this small value D here, okay? All right. First thing we'll do is figure out, obviously, how far the car will go, all right? Now, if we want to find S, there's 2 equations that will have S in them, okay? That's this last one and the first one, okay? This first one has S, U, T, and A. This last one has V, U, A, and S. We have our V, okay? It's going to be 0 because the car wants to stop, all right, and hit the brakes, right? We have our U, okay, and we have our A, all right? So what we can do is use the equation V squared equals U squared plus 2AS to find what that displacement is, at which point the car will stop, all right? So V squared, V is 0, U squared is 25 squared, 2A is 2 times -5, and S is what we're finding. It's -5 because it's a retardation. Now, this word actually means a slowing or a deceleration, okay? And it's used mainly in the context of dynamics, all right? But in this case, we can take it as being a -5 acceleration, all right? Okay. All right. So if we rearrange this, all right, we're going to get 10S equals to 25 squared, which is 625. All right. Therefore, S displacement is going to be 625 divided by 10, which is 62.5 meters ahead. Okay, so again, important to give a vector quantity a direction. So what we're saying is the car, when it hits the brakes from this distance, it'll only slow down for about 62.5 meters. Meaning, if S plus D equals 65, like we can see here, okay? And D is what we're finding, we can say D is equal to 65 minus S equals to 65 minus 62.5, which is going to be, let me move this around a bit. That's going to be 2.5 meters in front of tree, okay? All right, so a more complex setup, but only because we're being asked to find a quantity that's a little out of the way. So we've got to do some work to actually get to figure out where this lies in relation to the total distance and the car's braking distance S, okay? But again, all right, we're always starting with our variables, figuring out which of the 3 equations we can work with, And by the time that you choose equations, you can usually trial and error, or if you don't need trial and error, it kind of just pops out, okay? So always start with your variables, and with due process, you'll get the right answer. All right, next one. A train travels along a straight piece of track between two stations A and B. The train starts from rest at A and accelerates at 1.25 meters per second until it reaches a speed of 20 meters per second. It then travels at the speed for a distance of 1,560 meters and then decelerates at 2 meters per second squared to come to rest at B. Okay, so a lot going on here. So let's break it down. All right. So it's a straight piece of track between two stations A and B. So I'm going to draw this first. Here's A. Oops. And here's B. Okay. It starts from rest at A, meaning U equals 0. It accelerates at 1.25 meters per second. So I'm going to call this A1. Until it reaches a speed of 20 meters per second. Sorry, I'm going to make this U1 equals 0, A1 equals 1.25, and V1 equals 20. The reason I'm doing this is because we actually have two separate sections of motion here, because the acceleration is uniform for the first portion, but then it changes for the second portion of motion, okay? So I'm going to break up this line into two pieces. Oops. And then the second portion here. All right. So I'm going to call this change of a point y. Okay. All right. So first we've got to find the distance from A to B. All right. Now, this is going to be a case of finding each segment's distance. All right. The first part, okay, we're given the initial velocity, acceleration, and velocity. And we're also given the, that's all we're given. So we've got to find the S. All right, so we have V, U, and A. We're finding S. The equation we'll use is going to be V squared equals U squared plus 2AS. All right. So for A, Y, V squared equals U squared plus 2AS. V is 20 squared. U is 0 squared. A is positive 1.25. And we're finding S. All right. Now, if we rearrange that, okay, we're going to get 400 equals to 2.5 S. All right. And then S equals to 160 meters towards B. Okay. All right. So I'm going to call this SAY. So that's the displacement from A to Y. That's going to be 160 meters. Okay. Now, after it reaches 20 meters per second, it travels at the speed for a distance of 1560 meters. Okay. And then decelerates at 2 meters per second to come to rest at B. Okay. So we've got this portion Y, okay, that's 1560 meters long, okay. And then following this, we have a deceleration at 2 meters per second to come to rest at B, okay. So what we've got to find now is how long there is between Y and B, all right. So at Y, we'll call this U2. We're already at 20, okay? Our final velocity is going to be 0 to come to rest at B, and the acceleration is a -2 acceleration because we're decelerating. We're going to find, again, S, Y, B. We're finding. We found SAY, now we're going to find SYB, all right? Now I'm going to rub all this out and just leave SAY there, okay? So the second portion, the same formula, V squared, so YB, V squared equals U squared plus 2AS, all right? Final velocity is 0. Initial velocity is 20. acceleration is -2, and we're finding s, okay? Now if we rearrange, we're gonna get 400 equals to -4s, okay? Therefore, s equals to sorry, not -4s, positive 4s. 100 meters, okay? And that's SYB, okay? So to break this down, guys, the train is traveling between A and B. Initially, it accelerates to a certain speed, okay? Once it accelerates, it hits that speed after 160 meters, okay? So after 160 meters, it then stays at that speed for over 1 kilometer, okay? After hovering at that speed for over 1 kilometer, it begins to decelerate. So what we found is the distance it takes to accelerate, 160, and then again, the distance it takes to decelerate. And there's this middle portion here that it covers at the same speed, okay? So the total distance from A to B, so S A to B is going to be SAY plus SYB, which is, sorry, plus 1560, which is 160 plus 100 plus 1560. That's a total distance of 1,820 meters. Okay. So a pretty complex question here. Okay. So be aware that even though we're talking about rectilinear motion, where to use the Superbad equations, we need to have a uniform acceleration. That uniform acceleration might come in different portions, okay? So it's important to make a distinction between different parts of this and combine them into one piece of motion, okay? So 1,820 meters is our total distance. Part B, the total time taken for the journey, okay? The total time is going to be based on each segment's own velocities and how far they travel, okay? The first portion, 160 meters, is covered. We now know the final velocity, the initial velocity, and the acceleration, so the time is going to be pretty easy, okay? So I'm going to get rid of all of this for now. Actually, I'll get rid of this stuff. And then move this over to the side. Okay. So for A to Y, we actually have some choices here. We can either use V equals U plus AT, or we can use V squared, or we can use S equals UT plus half AT squared, because they both feature time, which is what we're trying to find. But the second equation is going to be a bit easier for now. Okay. Final velocity in the AY portion was 20. Initial was 0. Acceleration was 1.25. And time is unknown, okay? So if we rearrange, we're going to get time equals to 20 on 1.25. That's going to be 16 seconds, okay? 16 seconds. That's for AY. So TAY equals 16 seconds. We'll save that over here, okay? Now, this middle portion of 1,560 meters, the time is going to be a straight distance covered by a certain velocity. Time equals distance over speed, we call it, okay? So that's 1,560 meters, and we know that's at a constant speed of 20 meters per second. Okay, so that's going to be 78 seconds. Okay, so I'll take this, I'll call this time for Y, and I'll store this over here as well. This last portion, YB, okay? YB, all right, we can use the same formula, V equals U plus AT, all right? Final velocity was 0, initial was 20, acceleration is -2, we're finding time, okay? So if we rearrange this, we're going to get 2t equals 20 Therefore, t equals 10, okay, seconds. All right. So all up, we have our 3 sections and their times now, okay? So I can say total time equals to TAY plus TY plus TYB, which is 16 plus 78 plus 10, or 16 plus 78 plus 10, 104 seconds. Okay. Okay, now that was a little bit easier than part A, but as you can see, we've had to distinctly calculate 3 different things for the 3 parts, okay? So the average speed of the journey, okay, is gonna be a bit easier than that, all right? The average speed is just the total distance over the total time. So nice and simple, all right? If I get rid of this, total time equals, oops, get that back, 104 seconds, okay. So time equals 104. Total distance we got as being 1820, so average speed equals distance on time, which is 1820 meters over 104 seconds. That works out to be 17.5 meters per second, okay? And because it's average speed, we don't need to specify a direction, okay? All right, so quite a bit happened there. It's quite a complex question, so don't worry if you didn't understand it fully initially, all right? You can ask me about parts you're confused about later, all right? But all it really is a few different kind of questions altogether. So we're really doing 3 questions in one here, which makes it quite hard, but as long as you're careful and you know what you need, all the variables, you should be okay. All right, let's move on. Another graph question here. The velocity of an object over a certain period of time is graphed. Describe the motion of the object within these 90 seconds. So we're just describing the motion here, okay? Now, can you guys still see my screen, by the way? Yeah, okay, beautiful, all right. So on this graph, right, we have 3 portions of motion, or 4 really, right? We have this increase in velocity, all right? We have this flat portion, we have a downwards decrease, and then a curved portion, okay? So we've got to be able to understand what those 4 things mean, okay? So the first part is from 0 to 20 seconds, so we'll call it portion 0 to 20, from 0 to 20, okay? Now there's a uniform increase in velocity, all right? It's a linear increase in velocity, so we can say if the velocity is increasing at a constant rate, there is a uniform acceleration, okay? We don't need to calculate the number. You can if you want. We're being asked to describe the motion, all right? 0 to 20 is a uniform acceleration, okay? Now 20 to 40, all right? We have this flat portion here, okay? That tells you the velocity is not increasing or decreasing. So we have a stagnant velocity here. So we could say from 20 to 40, there is a constant velocity, all right? Now after this section, we have a decrease, but this is a uniform decrease as well, okay? So from 40 to 50 seconds, we can see the graph decreasing in a linear fashion, which is a uniform deceleration. Because we're moving in the negative direction, guys, our velocity is decreasing, which is a deceleration. Okay. And the last portion from 50 to 90 is this weird curve situation. All right. Oh, sorry. Okay, thought as much. Can you see all that stuff now? Okay. Sorry about that, guys. So yeah, I'm just reading out what we have going on in each section. All right. So from 50 to 90 now, this last portion, it's a curve. All right. Now, what does this mean for our motion? All right. We know that, first of all, the velocity is not increasing at a constant rate. It's increasing at an increasing rate. Okay. So what that means is if it's increasing faster and faster, that must mean the acceleration is increasing. Okay. So from 50 to 90 seconds, we have an increasing acceleration. Okay. All right. So not only is the velocity increasing, but the velocity is increasing at an increasing rate. Okay. And for that, that means an increasing acceleration. All right. Now you have to get quite familiar with interpreting these graphs. The reason I know all this is because it's a velocity time graph. And on a velocity time graph, okay, the gradient is acceleration. So if the gradient is increasing, the acceleration must be increasing. If the gradient is flat, the acceleration must be 0. Okay. Some basic advanced math stuff here, but if you're struggling with that, all right, let me know at the end and I'll try and cover some of that with you if there is time. Okay. All right. Last question for this portion. Okay. We have another graph. Consider the motion of the object whose velocity time graph is given in the diagram. Another velocity time graph. What is the acceleration of the object between times t equals 0 and t equals 2? Between t equals 0 and t equals 2, we have this uniform increase, don't we? Okay. We have this uniform increase in velocity. All right. So for A, okay, the acceleration, okay, given by the gradient, which is rise over run, or the velocity on time, which is going to be this point minus this point. So 8 minus 0 over 2 minus 0, okay, which gives me an acceleration of 4 meters per second squared in the positive direction, okay? Positive direction, because it's an increase in velocity, which is a positive acceleration, okay? That's A. What is the net displacement of the object between times t equals 0 and t equals 8? So we're using another feature of these graphs here, and that's area under the graph. So we know on our velocity time graphs, the gradient is our acceleration, but another feature of the graph we can use is the area under the graph, and that's going to give us our displacement, okay? So the area under a velocity time graph is the net displacement. So between times t equals 0 and t equals 8, here's t equals 8. This area here, okay, I'll use a different color actually. It's going to be our area under the curve, but it's also going to be our net displacement, okay? So let me get this a bit smaller. Okay. So for B, we're adding up two areas here. It's going to be the area of this triangle from 0 to 2 and this rectangle from 2 to 8. So area 0 to 2, it's going to be half times base times height, which is half times 0 to 2 is 2 base. Height is from 0 to 8, right? Times 8, and that's going to be 8 meters, all right? And the area from 2 to 8 is a rectangle, so it's going to be width times height, which is 2 to 8 is 6, and then from 8 upwards to 8, again, is another 8 meters increase in height. So we'll call that 6 times 8, which is 48 meters. So total area equals to 48 plus 8, which is 56 meters. Therefore, 56 meters positive direction. Okay, so this displacement is in the positive direction because our area under the curve is on the positive half of the graph. If these numbers were negative, we would have a negative displacement, but they're positive, so we can say it's 56 meters in the positive direction. Okay, and we got that just by adding up these portions of area. So I'll call this area 0 to 2, and this area 2 to 8. okay? All right, and that applies for any velocity time graph. The area under the curve is going to be your displacement, okay? And in this case, it's from 0 to 8. If I was asked for the area or the net displacement from 2 to 8, my area would not include the triangle, just the rectangle, okay? All right, let's move on. Okay, now we're going to look at adding perpendicular vectors. So when we're decomposing our vectors, okay, the word is decomposition, where we take a vector and we break it down into its x and y components, okay? We can use that to add together portions of vectors in a perpendicular fashion, all right? So x and y are two vectors. In order to find what they add up to, all right, we need to have a magnitude and a direction, okay? For the magnitude, all we do is we use Pythagoras and we do the squares of the x and y added together and square rooted, okay? For the direction, we use trigonometry. We're finding this angle here. We'll call it theta, okay? And we know we have opposite and adjacent here. So tan theta equals O over A, meaning theta is going to be tan inverse of y on x, all right? Conversely, if we want to split up a vector, okay, we can use trig again. We have theta here, all right? If I want to know what this vertical component is, I have O, I have H, so sine theta equals O on H. Therefore, O equals to H sine theta, or the Y component, we'll call it Vy equals to V sine theta. Same idea for the X component, but just cos theta, okay? This should be just some basic stuff for you guys already, all right? But if you have any questions with the maths, just ask me, and just got to make sure you're okay with your basic math in order to do well in physics, guys. So if you don't do advanced maths, you might have a bit of trouble, but you can still learn it pretty easily. All right. Okay, now adding non-perpendicular vectors, okay? For these vectors, all right, all we've got to do is, so it's the vectors V and these blue vectors here, all right? All we've got to do is break them up into their vertical and horizontal components. So we're decomposing each vector in order to make them have vertical components and x components here, okay? And so by adding up all the components, we're really adding up the whole vector, okay? So this is called the component method, where we break it up into components and add them together, all right? So we take all the x components of the vectors, add them up. Then we take all the y components and add them up as well. And by doing that, we're really adding up the whole vector, okay? Now, the magnitude of this resultant vector, again, is just Pythagoras, all right? And the angle or the direction, again, is Pythagoras, sorry, it's trig. If you just use the angle made between the two main vectors, okay? So here, we've got this change in, or we've got this, the difference in x, difference in y. So we're really using this angle here, okay, theta. Anyway, it'll make more sense in the actual examples, all right? So one, you are trying to cross a river that flows towards the south with a strong current. You start out with your motorboat on the east bank, desiring to reach the west bank, okay? Directly west from your starting point. So here's our river. It's flowing, a bit big actually. The river is flowing south, okay? The strong current. You are on the east bank here, and you want to get to the west bank here. So point A to B. If I want to get here, all right, which direction should I head out my motorboat in? All right, so what we're looking at here is our velocity vector and the river's velocity vector, okay? So I'm going to call this, C for current. So our velocity is really going to be this, our motion, us swimming, us rowing in the motorboat across the river, so velocity, and it's going to be the velocity of the river, okay? So we're adding up these vectors head to tail, okay? And we can see that our resultant motion is not really straight. It's not across from A to B. It's going to be more like this, okay? This is our resultant vector, okay? So we can see that if we just head out on this direction, we're not going to get where we want to, all right? So we've got to give it a bit of an angle, okay? And figure out which way we'll land then. So if we were to go ahead and turn our boat to face a bit more north, so we're facing this way, and we use our boat's velocity here, okay? And then the river comes along and pushes us this way, we actually end up going in a straight path, okay? So by rowing in a generally northwesterly direction, okay? So northwest will be this way because north is north, west is here. By rowing in this direction, okay, what we're doing is we're negating the effect of the river, because once we go a bit north, the river will take us a bit more south and we end up where we want to be, okay? So the answer here is going to be B, all right? All right, number 2. The x component of a vector is 5.3 units and the y component is negative 2.3 units. The angle that vector A makes with the x-axis is closest to, okay? So vector A looks like this, all right? The x component is 5.3, so I'm going to call this AX, and that equals to 5.3. The y component is, sorry, let me redraw this, okay? The y component is actually negative. What that tells me is it's going to the right, but also down, okay? So here's the x component again. AX equals 5.3. The y component is negative 2.3. So AY equals negative 2.3. So A will look a bit like this, okay? The angle the vector A makes with the positive x-axis is closest to. So the angle it makes with the x-axis is this angle here. We'll call this theta. Now I can transfer this AY vector to be also here, okay? The same thing, okay? So if we add up AX and AY head to tail, we get here the actual A vector, all right? Anyway, okay? So if we're finding this angle, all right, we have a triangle here with theta 2.3 and 5.3, and it's right angled, okay? So we can use trigonometry here. So tan theta is going to be opposite over adjacent, or 2.3 on 5.3. So theta is going to be tan inverse of 2.3 on 5.3, okay? Let me move this, oops. Let me move this over here, actually. Okay. So therefore, theta equals to, and the calculator, okay, 23.45 degrees. Okay. Oh, sorry, 46 degrees. All right. So now the angle it makes with the positive x-axis, okay, if we write it down, it's going to be D. All right. Number 3, when Jeff ran up a hill at 7 meters per second, the horizontal component of his velocity was 5.1. So immediately I can see that there's some kind of setup here with a hill and a slope. So I'm going to draw Jeff here. Is Jeff, or skinny. He's running up the hill at 7 meters per second. Okay. Now this hill has some angle with the ground. All right. And the component of his velocity that's horizontal is 5.1 meters, okay? So if I extend his vector here, here's 7. This portion is 5.1, okay? And we're finding the vertical component. Call that Jy. Here's J, and J equals to 7 theta, all right? So to find Jy, we've first got to find theta. And we can do that using the known relationship between J and Jx, okay? Jx, okay? So let me do this over here. All right. So we know Jx equals to J cos theta, and Jx equals to 5.1. Okay. J is 7, so 7 cos theta equals to 5.1. So cos theta equals to 5.1 on 7. Theta equals to cos inverse of 5.1 on 7. That works out to be 43.23 degrees. Okay. So I'm going to take all this, and now I can use that to find Jy. All right. Jy equals, oops, let me write that. Messy. Jy equals to J sine theta, which is 7 times sine theta. Now we know theta, so we're going to plug that in. 43.23. We get Jy as being 4.79. They're giving us the values of everything in 1 decimal place. So I'm going to turn that into 1 decimal place and say Jy equals to 4.8 meters per second. Okay. Yeah, you definitely can. So with Pythagoras, you're going to get the answer with a pretty simple method here, okay? But what I'm trying to show you is the decomposition process, right? So if you want to use Pythagoras, go ahead and do it. In fact, I would recommend, if a question allows you to, use it as soon as you can, okay? But the reason I'm going through all of this is to show you how we would go about decomposing it, okay? But Pythagoras is 100% the easiest way to do it here, okay? All right. Now, that is a pretty standard question. So this whole hill setup, I want you to ignore. Obviously, I've drawn Jeff here, but most of these questions are just a very straightforward vector decomposition question in disguise. All right, so go ahead and make a diagram, simplify it, and there should be no issues after you've drawn a simplified nice diagram, okay? Okay. I'm gonna need a few minutes, guys, having some issues with the iPad here. So take a few minutes, take a break if you need. All right, I'm just gonna get back to you and we'll continue from there. Remember, any questions you have, write them down so you can ask me at the end. All right, just hang tight. All right, sorry about that, guys. Just sorting out some stuff. Okay. So, all right, back to it. We're given three vectors that have components on the table. What is the magnitude of the resultant of these three vectors? All right. Now, we're told that we have x directions and y directions, but the only difference is some are negative, some are positive, right? So in order to understand, what the result will be, we don't need to worry about what direction it is, just need to know that some are negative, some are positive, okay? So the magnitude of the resultant for the x vectors, okay, is going to be, okay, the sum of all x, all right? So we're going to add them up like normal, 3.5 plus 2 minus 5.5, okay? So very straightforward. Because we know that there's a positive direction and a negative direction, okay, we straight up add them up and we're going to get 0, okay? So the resultant in the x direction is 0. The resultant in the y direction now negative 4.5 plus 0 plus 2.5, okay? That's going to give me negative 2, I believe. Yep. So negative 2 is our y direction resultant, okay? So now the resultant of these three vectors all up, okay, is going to be given by an addition of the x and the y component, right? So the y component is actually going down, okay? So y, okay? Except our x component is 0, okay? What that means is the magnitude does not actually include it, all right, at all. And so the answer is 2 units, okay? So dynamics, all right, contact and non-contact forces, all right. You should know this pretty much, all right? Contact forces actually have contact between two surfaces, whether that's air, water, or a solid surface, and non-contact is like gravity and electrostatic, all right? So weight and normal force. Weight is just the force of gravity onto the ground, and normal reaction is the equal and opposite reaction to weight and force, all right? Frictional force is the reaction to a pushing force on an object that has any kind of surface. And that's pretty much every object. So any real life object will have these rough grooves if you zoom in, all right? The frictional force will be given by the resistance between these surfaces and these surfaces, okay? Now, friction has this formula here, okay? But we can also understand it from the lens of net force. So this friction force, okay, has to directly oppose the pushing force if this motion is in a positive velocity as constant, okay? But I'll show you an example of that in a second, okay? So there's three types of friction forces. There's static friction, there's sliding friction, and there's rolling friction, okay? We're really only going to look at static friction and kinetic friction, okay? Rolling friction is more of an advanced idea that we're not going to touch on too much, all right? But for the purposes of physics, you're not going to see much different here, okay? First question, a stack of 12 books with an average mass of 312 grams. What would be the weight of this stack of books? So the weight, we know, is mass times gravity, except we have 12 masses here. So 12 masses of 312 grams each times the gravity of 9.8, okay? Now, let's convert this to kilograms first in order to get an answer in standard units, okay? 12 times 0.0312, 9.8, getting 36.6912. We'll leave it at that, okay? Or if we round it up to 1, we're going to get C, okay? Let's move on to a more complex question, just because we're running out of time. All right, a 12 kilogram box being pulled along level ground at a constant velocity, okay? So again, we're drawing a diagram to start with. Here's our box. It has a weight force that's partly given by 12 kilograms here, and a normal reaction force, which will be in response to the weight, okay? It's being pulled along level ground at constant velocity. That's important, okay, by a force of 38 newtons, okay? What is the coefficient of kinetic friction between the box and the floor? So as we know, the friction is going to oppose the direction of movement. So we'll draw our frictional force on the ground there. Now, typically we represent that with this curve F, okay? Now, there's a few things we know about the frictional force. first thing we know is frictional force is given by normal reaction force times the coefficient of friction, okay? But it's also to do with the net force on the object. If it's moving forward at a constant velocity, okay, we know from Newton's laws that a constant velocity or constant motion will have a net force of 0, okay? So if we sum all the forces in the x direction here, okay, it's 38 and the friction. So 38 minus friction is 0. So friction is also equal to 38 newtons, okay, equals 38. So if I know that Fn times our static friction coefficient is equal to 38, and I know Fn is equal to mass times gravity, because it's a response to a weight force, then mg times mu equals 38. I'm going to make some room here real quick. So mass times gravity times mu, so 12 times 9.8 times mu is equal to 38. And we're going to get mu as being 38 divided by all of that. So 38 divided by 12 times 9.8. That works out to be 0.323. Now the units for this is pretty complicated, so don't worry about units, although there is some standard units for this. Leave it as just a number, so 0.323, okay? So we're understanding that the coefficient of friction, or the frictional force altogether, is given by two things. There's one, this formula here for the net force times the coefficient, but also in an object that has no acceleration or a constant velocity, the net force is 0. Therefore, that friction that's opposing the pulling force has to be equal to the pulling force. Okay, let's move on. Okay, let's do this question here. All right. Okay, so it's a more complex setup because the force acting on it is angled at 22 degrees. Okay, computer base of unit of mass 4.5 kilos is dragged along a smooth desk. Okay, another setup of the box, except the force pulling here is by two arms, each with tension of 16 newtons. All right, so all up we have a pulling force of 32 newtons, and that's at an angle of 22 degrees. Okay, we also have, of course, our weight force, our reaction to the weight force, and our frictional force. Okay. Given all this, what is the normal reaction force? Okay. Here, we're actually going to use another version of this net force formula, and it's the net force in the y direction. So the net force in the y direction, in our case, will be given by three things. It's going to be the normal reaction force. It's going to be the vertical component of this pulling force. Okay. The vertical component of this, which is going to be up, as well as our weight force. So it's going to be Fn plus, I'll call this Ty, so Ty, minus the weight force, that equals 0. Okay, now we know that Fn and weight force are equal. Okay, so Fn, which is plus Ty, which is 32 sine 22, minus mg equals 0. So Fn then equals to mg minus 32 sine 22. Okay, I'll sub those values in actually. So 32, that's going to be a mass of 4.5 times 9.8, is minus 32 times sine 22. We get our normal force as 32.11 newtons. All right. So the way we went about this is understanding that we have three forces acting in the vertical direction, and due to there being no net motion vertically, the box is not jumping up and down. Right. We know the net force has to add up to 0. Okay. So we add up everything that contributes to this vertical net force, which is the normal force, the weight, but also a vertical component of this tension force. Okay. And by equating these, we can rearrange to make the normal force subject and get this value here. Okay. And we'll call that motion, or that direction, upwards. Okay. So 32.11 newtons upwards. Okay. I'm going to move on to this last section here, just because we're running out of time. Okay. Looking at work, kinetic energy, and just all kinds of energy, really. All right, power and impulse. All right, so these formulas are quite transferable, meaning the work formula is what the power formula depends on, and the energy formulae are going to be important in impulse as well. So just keep in mind that these 5 equations are a bit different to the Suvat ones in that we're going to be constantly using them in between one another. Okay. All right. Example 1, how much work is done on a lawnmower by a person if he exerts a constant force of 75 newtons at an angle of 35 below the horizontal and pushes the mower 25 meters on level ground? So here's our lawnmower. I'm just gonna make it a box, okay? And this guy's pushing at 75 newtons. Should I write this over here? 75 newtons at an angle of 35 degrees, okay? And the lawnmower travels 25 meters. Work is force times displacement, except we've got to make sure that we're using the force that's in the direction of displacement, okay? So we're going to try and get the x component of this pushing vector, okay? That's going to be 35 times cos 75, sorry, 75 times cos 35. Times our displacement of 25, okay? We're going to get, okay. $75 times cos 35. We get 1535.91, or if we rearrange that to make it in standard notation, that's D. Okay. So, yeah, in joules, because work is still in joules as force times displacement, and work is all in joules. Same with all the quantities in this module. All right. So just get used to writing in joules or kilojoules when asked to. All right. Okay. We'll do this question as well. A motor is rated at 5.6 kilowatts. How much work can it do in 20 minutes? Okay. So power equals to work over time. Okay. Equals to 5.6 times 10 to the 3, because we're working in kilos or kilowatts, which is a 10 to the 3 factor. Okay. The work done in 20 minutes, 20 minutes in seconds, it's going to be 20 times 60, is 1200. Therefore, the work will be 6.72 times 1, 2, 3, 4, 5, 6 times 10 to the 6 joules. Okay. All right.